Okay, good morning, students. So last time we were talking about quotient space of a non-linear space. So we have this theorem. Let V be a non-linear space and W be a closed subspace of V, then the quotient space V mod W. This is a non-linear space with norm of any element of the quotient space is of the form norm of x plus w, so its norm is defined to be equal to infimum of norm of x plus w, where w belongs to capital W. So with this norm, this becomes a non-linear space, and also V mod W is a Banach space if V is a Banach space. So if V is a complete nonlinear space, then the quotient space is also complete. So to prove this, checking that this defines a norm, that is not difficult. So I'll leave that as an exercise. Is a norm on V mod W is left as an exercise. So now we'll prove that if V is complete, then V mod W is complete. So assume V is a complete nonlinear space and let us take a Cauchy sequence in V mod W. We will prove that will converge in V mod W. So let xn plus W be a Cauchy sequence in V mod W. Then we have to show that this will converge. So first of all, we have to somehow get convergent Cauchy sequence in V, and because V is complete, then it will converge, and then we will show that this xn plus W will converge to that corresponding x plus W. So because this is a Cauchy sequence in V mod W, so then there exists a subsequence such that norm of x and k plus W minus x n k plus 1 plus W. This is less than 1 by 2 to the k. So this is a general thing. This is true for all k in n. So if you have any Cauchy sequence, then that says that for any given epsilon, now you can find some n naught such that if n and m are bigger than equal to n naught, then the distance between xn and xm will be less than epsilon. So to do this, what you can do is that first of all, if we take k equal to 1, so if I take epsilon equal to half, then there exists some point, say n1, such that if n and m are bigger than equal to n1, then xn minus xm, here it is xn plus w, so that difference norm will be less than half. So then so if I take that n1, then xn1 plus w minus any xm plus w, that will be less than 1 by 2 if m is bigger than equal to n1. So now what we can do is now take epsilon equal to 1 by 2 squared, and then for that there will be is again some n2 such that after that the difference will be less than 1 by 2 squared. So you choose n2 to be strictly bigger than n1, and then by the first condition we have xn1 plus w minus xn2 plus w, that will be less than 1 by 2, and then we have xn2 plus w minus anything which is bigger than equal to n2, so that will be less than 1 by 2 square. So then again you choose your n3 such that the difference will be less than 1 by 2 cube, and then by induction you see that you can get this sequence n1, n2, n3 and so on, such that this holds. So this you can prove. Now once we can do this, then okay, so we get this. So what does this mean? So this norm is less than 1 by 2 to the k. So this implies we can choose ynk, this in this coset x n k plus w, such that I can say just yk. So this I'll write as yk belonging to this x n k plus w, such that norm of, if I take yk minus yk plus 1, this is less than 1 by 2 to the k for all k. right? Because this norm is the infimum of all these things. So we can choose this such that this happens. Now, if we have this, what can we say about the sequence yk? So this will imply yk. This is a co-sequence in V. So we get a Cauchy sequence in V. This is again easy to show because we have the successive term, the difference is less than 1 by 2 to the k. So if you look at any yn minus ym, then because the geometric series converges, so you can make that less than any epsilon if you choose nm to be bigger than equal to some fixed number. So this becomes a Cauchy sequence, and since V is complete, this yk will converge to some converges to some y in V. So we get this yk converges to y. What does this imply? Therefore, if we look at now, this xnk plus w minus y plus w, this norm in the quotient space. What can we say about this? We know that yk belongs to xnk plus w. So therefore, this is less than equal to norm of yk minus y, and this goes to 0 as k goes to infinity. So therefore, this sequence xnk plus w this converges to y plus w in v mod w. So what we got is that the original sequence was xn plus w. We got a subsequence which converges. So hence the Cauchy sequence xn plus w has a convergent subsequence and which implies the sequence itself must also converge. Right, because for Cauchy sequence, if there is a subsequence which converges, then the sequence also converges to the same limit. So this sequence this also converge to y plus w. So therefore, we have proved that v mod w is complete. Is this clear?
Sir, can you again recall the how you are choosing YMs?
Which one?
YK sequence.
Yk sequence. Okay. So So let's look at this. So what we have this what is this norm? This is the infimum of, so this is same as xnk minus xnk plus 1 plus w, its norm. So that will be in the infimum of xnk minus xnk plus 1 plus w, where w belongs to capital W, right? So that is less than 1 by 2 to the k. So so you can find some point such that the norm is less than 1 by 2 to the k, right? So we'll get something like xnk minus xnk plus 1 plus some w, norm is less than 1 by 2 to the k. So then you just take your this yk you can take, for example, xnk plus that w by 2, right? Then this or yk you can take xnk plus that w, and yk plus 1 you can simply take xnk plus 1, and then this is true, right? So is this clear?
Yes.
So you try to write, so maybe this I'll write justify. Similarly, this one that I said that you can choose a subsequence like this also you can try to prove. So these are like general things about Cauchy sequence that we can do like this. Just 1 second. Okay, so next thing, let me discuss about completion. So maybe I'll do for metric space also, and then for non-linear space. So completion of metric space and a non-linear space. So first of all, what do we mean by completion of a metric space? So let's say X is some metric space. So a metric space X tilde, this is said to be completion of a metric space X if X tilde is complete and X is a dense subset of X tilde. So again, by this dense subset, what we mean is that I mean you can have a map from this X to X tilde. So I mean corresponding to every X in X, there will be an element in X tilde, and then basically that image will be dense in this X tilde. So you will see how we can construct completion of a metric space. So also one can show that in some sense this completion is actually unique, which means that if you get two different metric spaces which are completion of this metric space X, then there will be a, an isometry between them, and restricted to X, it will be identity map. So okay, so let's see how we can uh, define completion of a metric space. So suppose we have a metric space X. So suppose XD be a metric space. Now we define so first of all I'll define an equivalence relation. So for say Cauchy sequences Xn and Yn, in X define this Xn is equivalent to Yn if distance between X and Yn, this goes to 0 as n goes to infinity. Right. So if we take any two Cauchy sequence such that the distance between X and Yn, now this goes to 0, then we say that this Xn is related to Yn. So first of all, you can check that this tilde is an equivalence relation on the set of all Cauchy sequences. Right. Of course, this is reflexive, because if you take Xn and Xn, then the distance between X and Xn is 0. and symmetry is again by the symmetry of this metric. And if xn is equivalent to yn and yn is equivalent to zn, then distance xn yn goes to 0 and distance yn zn goes to 0. Then if you take distance between xn and zn, then by triangle inequality that is less than equal to the sum of these two distances and both go to 0. Therefore, this will also go to 0. So this is an equivalence relation. So let x tilde this be the collection of all equivalence classes. So this is, we write x mod this tilde, this is same as the collection of all equivalence classes of xn such that this xn is a Cauchy sequence. So in this equivalence class we take with respect to this equivalence relation that we have defined. So we have got a set. Now we will define a metric on this. So okay, maybe before like doing this, I'll explain you by an example that you are familiar with. So we know that R, the set of real numbers, that is a complete metric space. Now, if I take Q, the set of rational numbers, that you know is not complete. Now, what is the completion of Q is R. So, this is basically giving you a general construction how you construct the completion. So, you can construct this R from Q by using this process that we are discussing. So, how you can do? So, you look at, first of all, you have only set of all rational numbers. Now, on rational numbers, so you can define what we mean by Cauchy sequence. And of course, we have Cauchy sequence of rational numbers, which does not converge in a rational number. So, that is not a complete metric space. But now what you can do is that you look at the equivalence class of all the Cauchy sequences, and then you can define real number by limit of that. Basically, we associate with each Cauchy sequence a real number. So that way you can define a real number. So that is like one way of like defining real number. Other way you might have seen using Dedekind cut, we define real numbers. But you can do using these Cauchy sequences. So for every Cauchy sequence of rational number, you associate a real number, and then I mean, if you want to see how like then Q will be a subset of R, then corresponding to a rational number x, we look at the constant sequence x, and that Cauchy sequence that corresponds to the real number. So, in that sense, you can see that this Q will be a subset of R. So, okay, so here we have now defined a set, and then we will define a metric on this for these two, say xn and yn. belonging to x tilde define distance between these two. So let's call this capital D of, maybe I'll write these as some x tilde and y tilde. So if we take x tilde and y tilde in this capital X tilde, then distance between x tilde y tilde is defined as the limit of distance between x and yn as n tends to infinity. Right. So okay. So
But why will this limit always exist?
yeah, that is what I'm trying to like explain. So if you have, so this xn and yn are Cauchy sequences, and then we are taking the distance between x and yn. So
So D X and YN is a Cauchy sequence in R, and that's why converging.
ye so okay. Okay, let's try to see why this limit exists. So if we look at y limit of dx and yn exists. So okay, so let us call this alpha n is distance between xn and yn. Then alpha n minus alpha m, if we look at distance between x and yn minus distance between xm ym. And this is dxn yn, that is less than equal to distance between xn xn xm plus d xm ym so xn xm, then we take xm in say yn.
Yeah, I think we can take distance of xn to yn is less than equal to xn to xm plus xm to ym plus ym to yn. And so xm ym will cancel.
xm
Uh,
ym plus distance from ym to xn 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 ym. Right. So yeah, let me not put mod here. So if I do like this, alpha n minus alpha m, this is d of xn yn minus d of xm ym, and then by triangle inequality dxn yn is less than equal to dxn xm plus dxm ym plus dym yn. So the first one is less than equal to sum of these three, and minus we had d of xm ym. So this dxm ym cancels, and we get alpha n minus alpha m is less than equal to dxn xm plus dym yn. And similarly alpha m minus alpha n will also be less than equal to alpha m minus alpha n. This is also less than equal to d xm xn plus d ym yn. So therefore this mod of alpha n minus alpha m, this is less than equal to d of xn xm plus d yn ym. And because this xn and yn are Cauchy sequences, so this goes to 0, this goes to 0 as n and m goes to infinity. So this will imply that alpha n is a Cauchy sequence in R. Therefore, limit of alpha n exists. Right. So it needs proof, but that is just using the triangle inequality and that these are Cauchy sequences. So this limit dxn yn, this will always exist. Also, you should verify that this is well defined. That means that if you choose instead of this xn some other representative xn prime and yn prime for this yn, then if we look at dx tilde y tilde, here it will be dxn prime dyn prime. So the limit will be same. Right? So that is by using this equivalence relation, that distance between, if we take equivalent thing, then the distance between xn and xn prime, that goes to 0, and similarly distance between y and yn prime goes to 0. So using that you can see that so verify that this dx tilde y tilde is well defined. Let me just write what this means. That is, if sequence xn prime is equivalent to xn and yn prime equivalent to yn, then limit of d xn prime yn prime, this will be equal to limit dxn yn. Right. So it doesn't matter in the equivalence class which representative you are choosing, you get this limit is same, and therefore this dx tilde y tilde is independent of what you choose here. So this is well defined. And then we have to show that D is a metric. So D is a metric on X tilde. So of course D of X tilde Y tilde, this is always bigger than equal to 0. This is obvious. And if this is equal to 0, dx tilde y tilde equal to 0, this is if and only if limit of dxn yn this is equal to 0. But this implies this x tilde, which is the sequence xn, this is equivalent to yn, which is my y tilde. I mean, I should say only this, because this was the definition of the equivalence relation, right? Xn and yn, these Cauchy sequences are equivalent if limit of dxn yn is 0. So this is the same as this, and that is same as writing x tilde is equal to y tilde. Right? So dx tilde y tilde is equal to 0. This is if and only if x tilde equal to y tilde, and d of x tilde y tilde equal to d of y tilde x tilde. This is again obvious, because dxn yn is same as d of yn xn. And then triangle inequality. So d of, if I take x tilde and z tilde, this is limit n tending to infinity of distance between xn and zn. And d of xn zn, that will be less than equal to dxn yn plus dyn zn. So therefore, this limit will be less than equal to sum of these two limits, and limits all exist, so we get this is less than equal to d of x tilde y tilde plus d of y tilde z tilde. So this is the triangle inequality. So this is a metric that is again easy to check. Now we will have to show that this is a complete metric space, and then we have to see that x is a dense subset of this. So x tilde with this d is complete. So take any Cauchy sequence in this. So let me write this as x tilde k be a Cauchy sequence in capital X tilde. So I'm not writing here subscript because corresponding to x tilde you have a xn where we write as subscript. So I'm writing as superscript. So this is a Cauchy sequence in x tilde. So this element, suppose I take any xn. So we have xn k. This sequence is in this x tilde k. So we are taking corresponding to this x tilde k a Cauchy sequence in x. So we have this Cauchy sequence in x. Now what is d of x tilde of let's write k and l. This by definition is limit of distance of xkn and xln. So we are assuming that this is a Cauchy sequence. So that means that this goes to 0 as k and l goes to infinity. So that will imply okay. So let Right. So since x tilde k is a Cauchy sequence, so we can choose this nk such that distance between x k n no. So first, yeah, we are choosing this less than 1 by 2 to the k if n and m are bigger than equal to nk. This is because x k n, so I should write this. This xkn, this is a Cauchy sequence in x p. Right. So this for every k, this is a Cauchy sequence. So therefore, you can choose the nk such that uh, this can be made. So you take epsilon equal to 1 by 2 to the k, and corresponding to that, you get some natural number which we call nk, such that d of xnk minus d of xmk, this is less than 1 by 2 to the k if n and m are bigger than equal to nk. भी आ रहा हूँ, क्लास बस खत्म होने वाली है, ऑफिस में आ रहा हूँ. So now we write xk is equal to, so now we look at the nkth term of this sequence xk. So we look at xk nk. This is my small xk I am writing. So then if I write like this, then this xk, this sequence, this is for k belonging to n. If we look at the equivalence class of this will be in x tilde. This belongs to x tilde, and if we look at the distance between the original this and this, so and so if I look at d x tilde, comma, this let's call this as x. So x tilde k right. So this and this goes to 0 as k goes to infinity. So we are trying to like so that there exists some point in x tilde which is limit of this Cauchy sequence x tilde k. So where this x is nothing but this. So let's call this element x. So x equal to, I am writing this. This is in x tilde, and distance between this sequence and this, because this is equal to. So if you notice, what is this? This is equal to limit of distance between xk n and xn as n goes to infinity. And what we have from here, this maybe I should use a different notation. So it is better to write this as uh, okay, this is okay. So what we know is that distance of xkn and this xn is nothing but x distance between xkn and xk nk if I take, then that we know is less than 1 by 2 to the k, and then using that you can show that this distance goes to 0. So basically we want to prove that this Cauchy sequence converges to some point in this x tilde. So after that define a map phi from x to x tilde by phi of x is equal to, corresponding to any point x in capital X, you have the constant sequence x. So you write the constant sequence x and look at its equivalence class. So that is an element of x tilde. So phi of x is the equivalence class of the constant sequence x. So then this phi is an isometry. This is easy to see because if we take distance between phi x and phi y, that is by definition that is limit of distance between the nth term of this phi x and nth term of phi y. So that is same as distance between x and y. This is just by the definition of capital D. So this phi is an isometry from x to x tilde. So x can be considered as a subset of x tilde. So, so because this is an isometry, so it is 1 1. So therefore x can be considered as subset of maybe I'll write x tilde. So basically x we are identifying with phi of x. And then this x is a dense subset of x tilde. So basically instead of x I should say that phi of x that is a dense subset of x tilde. This is because if you take any yeah, so why is this? So if I take any xn just belonging to x tilde, and epsilon greater than 0, then I have to show that there exists a point in x or phi of x which is the whose distance is less than epsilon. So if we take anything and epsilon greater than 0, then there exists some n naught such that distance between xn and xm is less than epsilon for all nm bigger than equal to n naught. This is by the definition of that this xn is a Cauchy sequence. So we get this. Now if I look at so this implies also that distance between if I write xn and xn naught, this is less than epsilon for all n bigger than equal to n naught. So therefore if I look at the distance between this x tilde, call this element as x tilde. So x tilde and this phi of xn naught. So phi of xn naught is the constant sequence xn naught. So this distance is what? This is the limit of the distance between xn and xn naught, which we know is less than epsilon for all. So this will be less than epsilon. So what we have shown that if I take any point in x tilde then I get a point in X such that the distance of this is less than epsilon for any epsilon. So this proves that this phi of X is dense in X tilde. Okay, so I'll stop here. So this is the completion of a metric space, and then once we have this, then it is easy to like for non-linear space. So you can define a norm on this X tilde, the completion. That is by just taking the distance between, because if you have matrix which is induced by a norm, then norm of X is the distance of X to the origin 0. So by defining that, we will see that that will define a norm on this X tilde, and so that will be called the completion of the nonlinear space. So I'll finish that in the beginning of next class tomorrow, and after that I'll talk a little bit about convergence of series in Banach space. So in any non-linear space, we can talk about convergence of an infinite series, and then absolute convergence also. And then we'll see, just like for real numbers, you know that any absolutely convergent series is convergent. So that is true for any Banach space. If I have any absolutely convergent series, then it will be convergent. So that we'll do. Okay, so I'll stop here.